Bismillahirrahmanirrahim. Dear friends, this is our first video in the context of steel connection design. We will learn how to model and design this connection on the software IDEA Statica. This is the connection for the truss that we have designed in our steel design course using MIDAS GEN. Let me show you. This is the truss that we have designed in MIDAS GEN. And this is the truss that we are talking about. So this is the connection that will be designed by us in IDEA Statica. This is the bottom chord of the truss, and these two are the diagonal members, and this one is the vertical member. So we will design this connection using a gusset plate. So let's get into the software screen. Before getting started, if you are new to our channel, then please hit like and subscribe button and share as well with your friends, and let's learn structural engineering together. One more thing, we have already started design course related to reinforced concrete structures. If you did not watch those videos, then please go and watch those. Links of those videos I am sharing in the description of this video. So let's get started. This is the first screen of the software IDEA Statica when we run this. So just click on the connection. So these are all the predefined templates that we can use for different connection design. Today we are designing the connection of bottom chord along with its braces. So just select this one and select the topology. This is the bottom chord, but we don't want it bolted, so just select this one. This is the blank, this is the bolted, this is the directly connected by the weld, and this is using the gusset plate. So create project, and that template has been imported in the software like this. This is the interface of the software. So let me briefly describe about it. Under the design tab, there are different commands. The first one is the project items, in which there are 4 tasks. The first one is the EPS, in which we can do the stress strain analysis of the connection that we have modeled. The second one is the stiffness analysis. From this stiffness analysis, we can determine the stiffness of our joint, how much is the rigidity of the joint. The third one is the capacity design, in which find out the capacity of that particular joint. The second portion is the data, in which we can undo, redo and save our project. The third one is the labels. Labels means the members that we have shown, let's say CH, D2, D1. These are all the members name that we have defined here. Similarly, plates, let's say just only see this. So this is the tube, and this tube is composed of 4 plates, namely web 2, web 3, web 1 and web 4. What this software do is, it is discretizing all the members into some plates, and then it will analyze those members as a single plates and do the design. So these are the plates. Similarly, this is the LCS, the local coordinate system of each member. So we can see these are the local axes of each member, so we can toggle from here. The next tab is for the pictures that we can attach in the report. The next one is the template, in which we can create or use previously defined templates for the connection. Next one is the CBFEM. CBFEM means component based finite element method. This software designs the connections using this method. There are the 3 buttons: code setup, in which we can select the codes and all the associated properties with it, and calculate button, it will do the analysis, run the analysis. The next one is the overall check. Then the next tab is for the option, in which we can alter the different settings associated with this software, the loads in equilibrium, LRFD, ASD, whichever we want to use the method. The next tab is for the imports and export the loads, and the next tab is the new, the member, loads and operations. So these are the members. Members are those objects which carry the loads or which is used as a support. There are the three members. CH is the bottom chord, D1 is this bracing, and the D2 is the other bracing. So D1 and D2 carrying the loads, and the CH is acting as a bearing member or a supporting member. Because the loadings that is carried by these two diagonals is to be transferred to the bottom chord through the gusset plate, through this joint. So we have to design this joint considering this bottom chord as the support for these two diagonals. Similarly, loads effect, in which we can define the loads for which we have to design the connection. Now the third one is the operations. There are the different kinds of operations for our connection design. These operations are basically the toolkits for modeling different types of connections. Since we are not using these sections as our connection members, so let's go to our model and check the member sizes. These are the chords. So go to the properties. We have used HSS 152.4 by 152.4 by 3.2. These are in millimeters, and braces as 50.8 by 50.8 by 3.2. Okay, so just select CH. Let's first right click on this and rename it as bottom chord. Let's go to the add new square hollow section HSS. So we are using HSS, and let's search for bottom chord. This is our bottom chord. Similarly, click on this D1 diagonal 1 and search for our diagonal. Similarly, G2. Now this two members have already been active in this list, so just go and click. So from this we can rotate our model by clicking this one, or by rotating from our mouse button. Since we are having another member, the vertical one, so just right click on this member tag or go to this member plus sign. So this will add a new member. Right click on it, name it as vertical. Cross section is okay. Now let's just go to our model and just hide this, selecting this, activate only. From this we can identify the angles by use of some trigonometry. Go to the query and query nodes. 1000, this is 1200, so the angle is 50 degrees. Similarly, this is 1000 and this is 720, so angle is 35 degrees. This D1 is having the angle of 50 degrees. There are different kinds of angles, so you can trial and error, so you can find out which angle should be changed. Similarly for D2, beta angle is 180, it's already okay, just select it and 35. Alright, now let's select on vertical. Let's go to beta as 0, 90. There are the three visibilities. First one is the solid, the second one is the transparent, so that we can see what is behind the plates or behind our object, and the third one is the wireframe. This is the node, and these are all the single line members. Now, one important thing is that in the truss connections, all the axial forces must be concentric at a single point, and that single point should be this particular node. So we can see that these are the dashed lines, and these are all meeting at single point, especially for the truss connections. Now we will alter this plate. This plate are having the dimensions, and we can alter from this, but this is difficult to edit this plate because we will add some chamfers according to the orientation of these diagonals. So it is better to do in CAD and then import it in the software. So let's go to the CAD and draw the geometry. So this is the CAD. So let's just first select the units as millimeter, make sure, and select our suitable precision. Select a rectangle of any length, let's say 5000, and the depth must be 152.4. Now make a center line like this one, and from this particular node let's draw a line of any length, let's say 1000, and angle for a desired angle, let's say 50. Similarly for this diagonal, and 180 minus 35 is 145. Okay, so these are our center line. Since we are having 50.8 by 50.8 dimensions for our vertical and diagonal bracings, so we will make an offset of 25.4, half of the length. Okay, now make an offset of 25 millimeters from this top and just move this point from here to here. Similarly from this, and trim the remaining one. So this is okay. Now let's make an offset of 210 milli from this to this, and 135 milli from this to this. Now we will align our user coordinate system with this line. Type UCS, click here and the second point and enter. Now make a line. Now again here, so this is our plate. Now select these lines and press J, enter to join. Let's just copy this, again join. Now remove this one and move here. Now let's copy this and go to another file, open, make the unit as millimeter and paste it. Now we have to place this plate corner at origin. So to do so, just select a line starting from L, move. Now Control S and selecting as a DXF, and let's say Gusset 3. So this is saved. Just close it. No. Okay. Now go to our connection, click on this SP1. So what is the selected over here? It will be highlighted. So SP1, make it origin as a joint, go to shape, polygon, click on DXF and select the DXF that we have created, Gusset. So this dialog box is open. Check the units. It should be in millimeters. So click on this outline and click on the outline button. So the plate has been created. So just click on OK. So this plate. Now we have to set the orientation. RX should be 90. Now this plate center and this member center is aligned. So this member is having the depth of 152.4, and let's calculate the plate's depth. It's 81.45. 152.4 divided by 2 is 76.2, and 81.45 divided by 2 plus 76.2 is 116.9. So selecting this and make the Z offset as 116 and see is there any gap or not. So there is a gap, 115, so it is okay. We have to change the horizontal offset of this plate as well. So just go to the CAD, let's make a line, go to linear and center of the plate and center of this node. The horizontal offset is 37.5. Okay, so the plate center and this member center is not aligned. It's has an offset of 37.5. So go to this and make minus 37.5 and check this, because in our CAD it is at the edge. So just minus 37, minus 38, minus 38 is okay. Now what we do is that if we click on this solid, so we can see that these diagonals D1 and D2 is having welded connection with this gusset plate, but this vertical member has no connection with this plate. Why? Because this vertical was not in the template. We have manually edited. This one is the operation to actually connect this plate with this member. So let's right click it and copy. So this is the Gus 3. Now member T1 is overwriting, so just click on this and click on this vertical existing plate, and what is the plate is SP1 related to and related also to, leave it as blank. This gap should be 25. Why? Because remember we have set this distance as 25. Alignment is center, line plate no, okay. Now go to gusset, make it 25 as well. Now selecting this SP1, thickness should be 6 mm. Now go to gusset and make the welds thickness as 6. E70 XX electrodes to be used. We can see that these welds are on the both sides. Why? Because this is the check double fillet. If we select this single fillet, so it's only at this side. Okay, and if we select this double fillet, this fillet, so it will be on that side. Double fillet, it will be on the both sides. Make all the welds as 6 mm. Okay, now we can see that there is no connection between this SP1 and this bottom chord. So to make a connection, just right click on the operation, new operation, and there is an operation cut off plate. So select this and selecting this as a weld. Modified item is SP1 because we want to connect the plate SP1 and we want to connect this SP1 plate with this web, and this web name is web 3. We can see at the bottom. So bottom chord web 3. So this is okay. Now the connection has been generated. Just alter the thickness 6 mm and it's okay. Now we will add loads to our members. So to do so, just go to MIDAS GEN and activate all. So this all structure has been activated. So just selecting this view, and since we are designing this connection and this connection seems same. Alright, so let's just first selecting these members. If we select these members, so it will be selected from all the truss. Okay, so this and similarly from this, and activate all. Now since these members are having the property of truss, so just go to results, forces, truss forces. We know that the governing load combination is the load combination number 2, 1.2 dead and 1.6 live, and click on values maximum. Okay, positive value means the tension and negative value means the compression, so they are all in tension. So the maximum value is 25.3, so let's plug in as 25.3 in D1. So it's tension force, so it is away from the member. Similarly for the other members, this diagonal and this diagonal. The maximum force is 27.9 and it is the negative value, so let's just take it as 28. D2 minus 28 kilonewton. Similarly for the vertical, minus 8.3. Okay, and there are no other forces, so let's skip all these forces as 0. One important thing, just go to member D1. Since we know that we are only having the axial forces in this member, so we have to select our model type as NVY and VZ. It is freezing all other degrees of freedoms for these members. Similarly for D2 and for vertical. Now run the analysis, click on the calculate button. So it is showing the results as analysis has been performed 100% accurate. Plates is also okay and it is showing 0.1 and which is less than 5%. It is actually showing the plastic strain. The codal allowable value is 5% and we are having only 0.1%. Welds have been utilized 62.6%. Okay, and buckling and GMNA analysis we have not performed yet. So we can go to the check tab and click on equivalent stress. Since we are using 836 plates for all the members, 836 materials for all the members, and it is equivalent to 248 MPa. So we can see that our maximum stress reached is only 223.38 and at this particular point. But we cannot only rely on these results until we can see the deformed shape. The deformed shape is very much important for any structural analysis. So just go to mesh and click on the deform, and we can see that the deformed shape is predictable. Since this is a compressive load, so it's something like that. This is not a buckling actually, because this is 10 times zoomed deformed shape. The scale factor is 10 times. Okay. Similarly, we can see the plastic strain. Only at this particular point we are having the 0.1% plastic strain. At the other point it is actually 0. Okay, so in this way we can design this connection. We can generate the report as well. Just go to the reports. So it has created a report in which all the details associated with this connection design has been included. We can alter this by selecting the items in the report as current, all and selected one. We can also include all the detailed formulations and explanations in our report by clicking these two buttons and click on refresh. Now we can see all the formulations associated with this connection design. We can also include the detailed drawings by clicking this button, bill of material, the tables of items and detailed drawing. We'll click on refresh. We can see now this is the gusset plate drawing. We can export this report to Word document, PDF document, or we can export these drawings to DXF. So this is up for today. In the upcoming videos, we will design other remaining connections of this truss shed using IDEA Statica. If you like our video, then please hit like and subscribe button and share with your friends. And you can comment below for your desired content or desired videos. I will try to make that content for you. So see you in the next video.